I'd like to now discuss the conservation of energy or the work energy theorem when we're moving in two dimensions or maybe three dimensions or any number of dimensions. I hesitated to do this segment because I know that Calc 3 is not required for this course, but I will give it to you anyways. Uh, if you can follow it, great. If you cannot follow it, well, you know what's coming ahead. If you will see the topic that I'm talking about when you have Calc 3, if you do take it. So, um, I hope you can follow it. Just try to follow as much as you can, and don't be intimidated by the math. I think it's very intuitive. All right? So let's do this. So remember, we said if you have the magnitude of a vector, a vector squared, let me write vector A dot A is equal to the x component of A times the x component of A plus the y component of A times the y component of A. I was just doing two dimensions, but it works the same way in 3D. So this is just ax squared plus ay squared, which is simply the magnitude of a squared. Because remember, how do you find the magnitude of a vector? Remember how you find the magnitude of a vector? It's simply you take the x component, you square it, you take the y component, you square it, and you take the square root. So this is just this part without the square root, right? If you take the square root away, you get this, okay? So let's start with the definition of kinetic energy. We know that the kinetic energy is defined as 1/2 of the mass times the velocity squared. Let's take our object to be moving along the xy plane. This is x, this is y, this is the x, this is y, right? And so the object maybe starts here, and so its position is R1, this is the position of the object, and then the object moves along this line, or this curve. So the position of this object at this point, maybe R2, and this is delta R. This is delta R. This is delta R. As you notice, to find the work done by the force, what you have to do is you find the force, you multiply it by delta R, and you integrate. So let me show you why that is the case. So this is the kinetic energy. Let me take the derivative of the kinetic energy with respect to time. But before that, v, the velocity, will have an x component and a y component, which means that this is 1/2 it's a vector, and the vector squared is the vector dotted with itself. So it's v dotted with v. Dotted with v. Let's take the derivative of this with respect to time. So dk, how does the kinetic energy change with time? So it will be 1/2 m, and I'm taking the derivative of this right-hand side with respect to time. So it's d dt of v dot v. You might be thinking, how does the derivative of a dot product work? Just like how you do the product rule. So it will be the derivative of this times this plus this one times the derivative of this one. So let's see how it works. So it will look like this. It will be 1/2 of m, and then the derivative of this first. So it will be dv dt, don't forget the dot product with v, and then plus this one, v dotted with the derivative of this one. So it's dv dt. dv dt is the acceleration. And notice that dv dt dot v and v dot dv dt, dot products commute. It doesn't matter the order. A dot b equals to b dot a. So this is just twice this quantity here. So this is just, this would be twice, it would be 1/2 of the mass times twice what? Twice this quantity. dV dt dotted with V. Dotted with V. The two cancels, and you get, what do you get? M times dV dt. dV dt is the acceleration. So that's the mass acceleration. Dot product with what? Dot product with V. With V. Right? With V. And remember what V is. It's the rate of change of position with respect to time. So I think this would put everything together for us. So let me just summarize here. So we have dk, the rate of change of the kinetic energy with respect to time is equal to ma, but what's ma? Ma is the force. That's the net force on the object. Dot v. Right? This is also, we know it's the power. So I'm going to write this on the next board, the same expression. So I have dk dt is equal to f dv, f times v, but v is dr dt. So now I want just dk. So dk is dk dt dt. But dk dt is f dr dt times dt. So what is f dr dt dt? Well, the dt goes away and you just have f dot dr. F dot dr. So this is dw. This is how much work you do in an amount dot dr. So this is dw. So let's integrate both sides. So we integrate both sides. So I have dk is the integral of f dr of f dr. All right, so I have this. So remember what we're doing. This is x, this is y, and we're moving from this point to this point. From point 1 to point 2, right? From this point to this point, along a certain path, right? So, let's say the kinetic energy at this point is K1 and the kinetic energy at the end point is K2. So the integral of dk is K evaluated between points 1 and 2. So this is just the change in kinetic energy. This is just K2 minus K1 as usual. And it's equal to the integral of f dot dr integrated between position 1, this is R1, and position 2, R2, and R2. So, okay, well here's the problem. When we were in one dimension, to move from here to here, you only had one option. You have to go this way. But in 2 dimensions, you have far, far, infinitely many paths. You can take this path. You can take this path. You can take this path. Or anything in between. You can go this way. So with this expression, this, how am I going to evaluate this integral if I don't know the path? If I just know the 2 endpoints? How am I going to even evaluate this integral? All right, so think about it. There are infinitely many paths. You tell me you're going from here to here. That's not enough, apparently. Or it seems like it's not enough. So how am I going to get there? How do I evaluate the work? How am I going to evaluate this? The answer turns out, just how we had the fundamental theorem of calculus for just regular integrals in 1D, there is the fundamental theorem of line integrals which works in multiple dimensions. And it says, for a certain class of forces that come from the derivative, more precisely the gradient of a function, they are path independent. The amount of work that you do going through a straight path or a curved path or any other path does not matter. It only cares about the endpoints. So if f is equal to the derivative in some sense, because here we have two variables, you have a function of two variables, it depends on x and y. If f is equal to the derivative of this function, so how are we going to do the derivative of this function? Well, the derivative of that function turns out to be, we will give it this symbol. It's, if f is equal to negative, you have this triangle here, it's called the gradient, del, of u. What does this mean? What does it mean? Well, this symbol simply means this. If you have a function u, and you want to take its, this is called the gradient, then you do the following. I'm sorry, this is forces vector. This is a scalar. So how do we, what does this symbol mean? Well, it just says it's equal to the derivative of u with respect to x. It's called partial derivative, because you hold y constant and then you just take the derivative with respect to x, I hat, and then du. And let me, instead of d, it's like a curly d, so it's partial. They call it partial derivative. Partial derivative with respect to y j hat. That's what this means. That's what this means. So it says, if our function f comes from such a gradient of a function, then we're good to go. Then this is simply equal to u, well, I have a minus sign because of the definition over here. Minus sign. It's equal u at position 2 minus u at position 1. You're good to go. And you end up with minus u2 plus u1 plus u1. And now you can get a conservation, because if you group the 2's together, so you'll have k2 plus u2 plus k2 will equal to k1 plus u1. I know I kind of hesitated, rushed, I didn't do it properly. You will learn about it in Calc 3, but I just wanted to show you that. So let me show you this in the context of just a generic function and then for gravity. Suppose you have a function u, and u is, let's say, x squared times y plus 3y times x. All right, 3y times x. How do I get this gradient of u? Well, I know that if, what does this mean? Gradient of u is equal to du dx I hat plus du dy j hat. Let's see how we compute this. What is this partial derivative of u with respect to x? Partial derivative with respect to x, it means assume y is constant, just hold y constant and take the derivative of x. So if y is a constant, we hold it constant, take derivative with respect to x. You get 2x times y, right? Assume y is like the number 7. So you get 2y times x. So you will get 2xy, and then take the derivative of this one with respect to x also. Y is constant, so you will just get derivative with respect to x. X goes away, and you just have 3y plus 3y. That's this part here, and then I hat. And then plus this derivative with respect to y now. You hold x constant now, and you take derivative with respect to y. If you take derivative with respect to y of y, you just get 1, and you have the x squared. And then the derivative of this with respect to y, the y goes away and you just have the 3x, so plus 3x j hat. This is the gradient of u. And so the force is minus gradient of u, and it will just be the negative of this thing. So let's say if I give you a force, and that force is negative 2xy plus 3y I hat plus x squared plus 3x j hat. This is called a conservative force because it's path independent. It does the same amount of work if I go from here to here along this path, or along this path, or along any other path. It will give me the same amount of work regardless of the path taken. That's called a conservative force. Another way to view it is it does zero work if you go on a closed path. If you go from here and come back to the same point, it does zero amount of work. It's another way to say it. Because I will explain this one more time later. Because if you go from here to here along this path, is the same work as going, let's say, along this path. If you go around a circle, you do positive work here, but then when you're going, you reverse the path. You're going this way now. So that's equal to the negative of this work. But this work is equal to this because we said it's path independent. So when you add them, you just get zero. So that is the force here. And it's a vector force. All right? So if you have a force like this, then you know that it is a conservative force. For example, gravity is a conservative force. Why? Here's the reason. What is the force of gravity? Well, the force of gravity near the surface of the Earth is F equal to minus mg, and it's in the y direction, right? It's in the negative y direction. So this force is a derivative of another, of some function that gives me this. That function is u equals to mgy. Mgy. Why? Because take the derivative of u with respect to y. Take derivative of u with respect to y. Force is minus, and here I don't have x, so it's just du dy. And so it's negative mg. Negative mg. And it's in the y direction because I'm taking derivative with respect to y. So gravity is a conservative force. Gravitational force is a conservative force. The spring force is also a conservative force. And we call this here the gravitational potential energy. You can add an arbitrary constant to it if you like, because once you take the derivative of the constant goes away and you get the force. It's unique up to a constant, an arbitrary constant. But we call this the gravitational potential energy. And this is why and we say that from earlier, we said that the kinetic energy at the end plus the potential energy at the end will equal to the kinetic energy at the beginning plus the potential energy at the beginning. This is the law of conservation of energy. Assuming the force is path independent, it does the same amount of work regardless of the path. The problem with friction is it does the amount of work that friction does will depend on the path. For example, if you go from here to here, if I rub my chuck, so friction has been doing work, and that work is equal to the normal force times mu k opposite this direction. So the work done by friction will equal to the force of friction times the distance traveled, and it's negative because it always acts in an at 180. However, if I take this path, friction is doing work, it's doing work, and it's doing work, and it's negative, 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 and it is negative. And when I come here, friction did a whole lot of negative work. From here, even though this is the initial point, this is the final point, whether I went this way or I went through this longer path, friction did more, different amounts of work. Gravity, on the other hand, it doesn't depend on the path. If I'm moving this way, the force of gravity is acting down, so it's doing zero work, because remember, work is force times displacement times the cosine of the angle between them. That's what the dot product. If you're moving this way, gravity is downward, and so it's doing zero work. Gravity will do positive work as the chalk is coming down. It will do negative work if I'm lifting the chalk up. Why? Because if I'm lifting the chalk up, in what direction is the motion? Well, it's upward. In what direction is gravity? It's downward. What's the angle between them? It's 180. And so you will get negative work. All right? So now I want to go to the end of this chapter, do a few examples, and then move on to chapter 10. Okay, let's look at this next example here from, or the last example from the chapter, and then I will look at examples or problems from the end of the chapter. So here we have a 25 centimeter long spring. So let's draw something here. Here is the spring, here is the floor, and here is the spring. The spring is here, and this is 25 centimeters. Or let me write it as 0.25 meters. Okay? All right, so what happens? Stands vertically on the ground, and then a 1.5 kilogram brick is held 40 centimeters directly above the spring. So here is a brick. It is 1.5 kilograms, and it is at a height here of 40 centimeters above. So it is 0.4 meters. Okay, sounds good. And then the brick is dropped, so this initial speed of the brick is 0. And then it compresses the spring to a length of 17 centimeters. So what happens? All right, so here's what happens. You drop the brick hits the spring, and then compresses it. It comes to rest momentarily, and then the spring tries to push it back up. So they say here, before the spring, before starting to launch the brick upward, so the spring compresses to 17, and then it's ready to launch it backward. And so let's see what happens. So we get this. So now the brick is here. There's the brick. So this is now 17 centimeters. The spring is 17 centimeters. So how far did it compress? Well, it compressed by, well, let's write it. This is 17 centimeters, 0.17. So this is what? 25 minus 17 is what? 8, I think? Yeah, 8 centimeters, or 0.08. 0.08 meters. And so, all right, sounds good. And then it says, what is the force constant of the spring? Oh, okay. Well, we have a mass. What is the kinetic energy here of the mass? Kinetic energy of the mass. We're in the chapter of energy. We could use Newton's laws, but let's use the conservation of energy. So the kinetic energy at step 1 is equal to 0 because the mass is not moving. And then the mass drops, hits the spring, compresses it, and then again it gains speed, and then it hits the spring, and then it comes to rest again because gravity is pulling it down, but the spring is pushing it up. And the more the spring compresses, the higher the force with which it pushes up. So here, the kinetic energy at the end is equal to 0 also. So that means, remember, the kinetic energy, the change in kinetic energy, is equal to the amount of the work done. That's the work energy theory. But this is 0. So that means the total work done is 0. So 0 minus 0 is 0, so the work done will equal to 0. Who is doing work? What are the forces on this mass? Well, you get gravity, and then you get the force of the spring. So gravity. So first of all, as the mass falls, the direction of motion is this way. gravity pulls this way. So they are parallel to each other. So let's calculate the work done by gravity. It will be the force of gravity times the magnitude of the displacement times the cosine of the angle between them. Both are downwards, so the angle between them is 0. They are parallel to each other, so that's 0. So let's calculate, this should say W, the work. Okay. So the work done by gravity will be force of gravity, that's mg, mass times gravity. So the mass is 1.5 kilograms. G is 9.8. The distance moved. How far did it move? Well, gravity has been pulling it from the initial position to the final position where it compressed it. So all the way from up here to here, gravity has been acting. So what's that distance? Well, it's the 0.4 plus the 0.08. So 0.48, right? So 0.4 plus some more, 0.08. So 0.48, 48 centimeters. So that's 0.48, 0.48. And the cosine of 0 is 1. So that's fine. And I'm looking for my calculator. I don't have it. Where is it? Let me borrow a calculator and come back in a moment. So I got a calculator. So we get that the work done by gravity will equal to, let's multiply through. You get 1.5 times 9.8 times 0.48, and that gives me 7.056. What are the units for work? They are joules, units of energy. Now, what's the work done by the spring? Well, as the mass, first of all, when the mass is here, the spring has not done any work because there is no contact between the mass and the spring. The spring starts doing the work when the mass hits the spring and it starts to compress. So the spring has done work for 8 centimeters only. And the force of the spring is not constant. So let me write it down. The work done, dW, for the spring. See here, I didn't have to do dW because the force of gravity is constant near the surface of the Earth. But the force of the spring depends on how far you compress or stretch the spring. So ds would equal to the force of the spring times the displacement, and then times the cosine of the angle. Times the displacement here. Let's call it dx or dy since we're in the y direction. Let me call it dy since we're in the y direction. And then times the cosine of the angle between the force and the displacement. Notice, when the mass hits the spring, the force of the spring is in this direction, the force of the spring, and it is equal to K times the amount by which you compress it, Ky. And then the displacement is this way, the spring is getting compressed. The mass is moving downward, but the force of the spring is upward. So the angle between them is 180 degrees. And to get the total work, you have to integrate. Okay, so let's see. So the work done will be this integral here, and I'll put K here, and then Y for the force of the spring, Ky, and then dy, and then the cosine of 180. What is the cosine of 180? The cosine of 180, this is 180 degrees. Cosine of 180 is minus 1. The cosine of 180 is minus 1. And so I get negative. Negative, yeah. And how are we going to, where do we integrate this from? We integrate from where to where? Well, the spring, this is the 0 position for the spring. It's neither stretched nor compressed, all the way to this, all the way to 0.08. So from 0 all the way to 0.08. All the way to 0.08. Yeah. Okay. And yeah, sounds good. So let's integrate this. K is a constant, so it comes out of the, here, comes out. And then the integral of y dy is y squared over 2. Y squared over 2. Let me put the 2 here. And we evaluate this between 0 and 0.8. And so I get that the work done, I should say SP here for spring, SP. So the work done by the spring is equal to negative 1/2 of K times 0.08 squared. And then minus the function evaluated at 0, which is 0. So it's just that. That's the work done by the spring. But now, the work done by the total work is equal to 0. So the work done by gravity plus the work done by the spring equal to 0. So I get the following. So the work done is equal to the work done by gravity plus the work done by the spring. So this whole thing will be 0. And so I get the total work, I get the work done by gravity is 7.056. The work done by the spring is negative 1/2 K times 0.08 squared equal to 0, and you solve for K. Let me get my calculator again. So I get 2205 newtons per meter for the spring. All right, you get to now the next problem.